molar heat capacity of the gas. See, the same thing we are discussing for solid and liquid when it is known as a specific heat. So molar heat capacity of the gas, or in the case of solid or liquid, we write dq is equal to mc d theta, where C is known as a specific heat for solid and liquid is there. And it has at constant temperature, suppose if it does not change, then the value of C is unique for solid and liquid, right? But what is happening, the same thing when you are coming for the gas, then the value of C is not constant, right? So for the gas, C is known as molar heat capacity. Molar heat capacity. It depends on the process. So suppose if anybody will ask you, what is the molar heat capacity for helium gas, you cannot have the answer until unless the process is not defined, you cannot have the answer is there. So this is the process dependent molar heat capacity is there, right? The reason is, suppose if you write dq is equal to mc d theta, then from C is equal to dq by m d theta is there. So if suppose isothermal process is there, isothermal process, then d theta is equal to 0. So C is equal to something dq by m into 0. So this tends to infinity. And if you think for adiabatic process, so that is if dq is equal to 0, then C is equal to dq by m d theta. So this is 0 by m into d theta. So this is 0. So the value of C varies from 0 to infinity for any gas is there. So it has no any specific value like solid or liquid is there, right? So for solid or liquid, we have a specific value is there, but for gas, it is process dependent. Okay. So now question is there, how one can search the value of C for any process. See, for known processes, see for at constant volume or constant pressure, right? So first at constant, at constant volume, this C is known as CV, which is R upon gamma minus 1. Gamma is the ratio of Cp by Cv, all of you might be knowing, or this value is 5 by 3 for monoatomic, and it is 7 by 5 for diatomic, and 4 by 3 for polyatomic, right? And sometimes when there is a mixture of gases, then gamma can change. It depends on the number of moles, how much one gas is mixed with another gas is there. So this is at constant volume, and in a similar way at constant pressure, this C is written as Cp, which is gamma R upon gamma minus 1. So that is, there is no only two processes are there, so many processes, and for every process the value of C is different. So now I am going to teach you how one can search the value of C for any gas, for any process. So we write, so how to find the value of C for any process. So we start dq is equal to du plus dw. All of you might be knowing first law of thermodynamics. And then we write nc dt and cv dt plus p dv is there. Or since PV is equal to nRT for ideal gas, so from here P is equal to nRT by V. So we can write NCDT and CVDT divided of P nRT by V dV. So one can write further this equation and we can get the value of C. Just I am writing the further how one can calculate the value of C. In most of the examinations, people are using the value of C is there. So from here, from at this place we can write the value of C. So you have to divide by n dt throughout. So from this place we can write at this point the value of C, Cv RT by V dV by dt. So this is the calculation you have to do for any processes there, right? So for different processes its value is different. So let us take one example. Question is there, find the value of C, that is molar heat capacity for helium gas for the process P is equal to alpha V. Alpha is any positive constant, P is the pressure, and V is the volume is there, right? So for this process I want to calculate the value of C. So C, I have to calculate this. So C is equal to Cv plus RT by V dV by dt. So see, I want to calculate dV by dt. It means what? I need relation between volume and temperature. But see, at this point I have given relation between pressure and volume. But I want to calculate dV by dt. Hence our relation should be between volume and temperature. So I want to eliminate P by, so P is equal to alpha V and PV is equal to nRT. So I want to eliminate P. So P is nRT by V, T by V, alpha V. So from here, so now I can differentiate. With respect to temperature, so that I can get the value of dV by dt there, right? So dV by dt I want to get. So one can calculate from this equation very easily. Just I am showing you how one can calculate the value of dV by dt. So already I wrote the equation at this point. So see, at this point, so now I want to calculate dt by dv is from here. So dt by dv is equal to 2 alpha v by nr. 2 alpha v, so v square is equal to, right, 2v, so 2 alpha v by nr. So I have to calculate dv by dt. I do not want dt by dv, I want dv by dt. So inverse of that, so dv by dt is equal to nr by 2 alpha v. nr by 2 alpha v, and I want, so therefore RT by V dV by dt. So this is RT by V and dV by dt. From this point is the nr by 2 alpha v. nr by 2 alpha v. So from here, alpha v square, right? So see here at this point, alpha v square is equal to nRT. So alpha v square is equal to nRT. So therefore RT by V dV by dt is equal to how much? R by 2. And since the gas is helium, so Cv is equal to R by gamma minus 1. So R by 5 by 3 minus 1. So this is nothing, 3R by 2. So therefore C is equal to Cv plus RT by V dV by dt. So this is 3R by 2 and that is R by 2. So this is 4R by 2. So this is 4R by 2. So one can so 4R by 2. So this is 4R by 2. So 2R. So therefore, for this process, the value of molar heat capacity is how much? 2R is there. So for any process, we can find out the value of molar heat capacity for the gas, which is process dependent. And whenever you want to calculate, then C is equal to Cv plus RT by V dV by dt I have to calculate, and we can have the value of C for the gas. Okay, thank you.